So this is a spring-loaded dart gun that's being used to shoot a little tiny dart vertically. So let's say this dart shoots up, and let's say it goes up a total height of 5.8 meters before it stops. And let's say the dart is, we'll make it a pretty heavy dart so the numbers will be a little bit nicer, 0.16 kilograms. That's a really, really heavy dart, but that's okay. And to do this, inside this little toy gun, there's a spring inside this gun. You can't see it, but there's like a spring inside that's being used to actually shoot the dart. And let's say it was compressed. Let's say it was compressed 4.5 centimeters in order to shoot the dart. Now we're going to find out a couple things. We are going to find out how fast the dart came out at, and we're going to find out the K value for the spring. Now, this is a basic energy type question. Now, we have three types of energies involved. At the very, very bottom down here, we have potential energy in the spring. So this is elastic potential energy. As soon as it shoots, that energy turns into kinetic energy when it launches out. And then as it goes higher and higher and higher, obviously it slows down, it loses kinetic energy, and that kinetic energy turns into gravitational potential energy. And at each of these three locations, here and here and here, all three energies have to be equal, because down here it's all elastic energy before it's shot. Right when it's released, it's all kinetic energy. And at the very, very top, when it's at rest, it's all gravitational energy. So those three energies have to be equal. So if I can find energy at one place, I can find energy at all the places. Now, I can't find the elastic energy, I can't find the kinetic, but I can find the energy at the top. I can find out the gravitational potential energy of the dart when it actually started. So I've got the mass of the dart, so I got the 0.16 times that by gravity, which of course is 9.81, and we times that by the 5.8, and we've got about 9.1 joules of potential energy at the top. And since that's the total energy, I can take that energy and I can put it anywhere I want. I can take that energy and put it over here where it'll be kinetic energy, and I can also take it and I can put it over here where it's going to be elastic potential energy. So I can just finish this thing off relatively easily then. So when it's being shot out over here, I want to just take that 9.1 joules. I know it has to be 9.1 joules. That has to be equal to 1/2 mv squared. I know the mass of the dart. I know the kinetic energy, so I can easily piece this together. And do not forget to square root your answer when you get it, otherwise it's not going to work out very well. So I get a speed approximately of 10.7 meters per second. So this thing fired out at around 10.7 meters per second and then went the height of 5.8. Now I can also take that energy, that 9.1 joules, and throw it all the way back where it began at the inside of the gun where there's a little spring that shot it in the first place. And I can use this to find out the K value for the spring. So once again, it's going to be equal to the 9.1, and I can use my spring expression, 1/2 kx squared. I know the x value, that's my 4.5 centimeters, so I can solve for my K value. So I got the 9.1, so times by 2. So it's actually a very similar calculation to the speed calculation. Again, don't forget to square the distance, and don't forget to put it into meters, and then we can calculate the K value. And once we do all that, we will get a K value of around, well, we'll round off, around 9,000 newtons per meter, which seems really, really, really high. But look at the units. It's 9,000 newtons to stretch or compress this thing an entire meter. Obviously, it's not even close to that. But that's what the K value is done reference to as per meter. And that's why the values can seem really, really high, even though the springs can be relatively small, because they take into account how much force to go an entire meter if it was physically possible. Okay, so this is just a basic conservation of energy type thing, incorporating the elastic energy we've been looking at. Once again, once you get the total energy one place, you can put it anywhere else you want, and you can calculate individual components of energies. So now let's look at another scenario combining different kinds of energy. And here's a really common toy that's out there. Basic Hot Wheels toy where they have a little tiny spring launcher to spring launch the car. Car comes up and goes over a ramp. So we're going to have our car come in here. And we'll take the car and we will have the car come down here. And it is going to, and then jump. Okay, and then keep on going. And we're going to find out a couple things about the situation. Now, first things first, let's do a couple of things about the car. Hot Wheels car, probably around 35 grams for a Hot Wheels car. This little yellow thing right here is actually pushed back, and it was probably pushed back, well, let's just go with 5 centimeters. So that's the X value for the little spring launcher, and then shoots it. It's going to hit a ramp, and then it's going to jump up, which is basically like a little projectile. And we're going to find out a couple things here. And let's say that the car jumps up and maybe goes a vertical distance of, well, let's go with, let's say 20 centimeters. Okay, so it's going to go 20 centimeters into the air, right? And we're also going to find out how fast it's going up here once we have the K value for the spring. Now the K value for the spring, all right, K value for the spring. We'll say the K value for the spring is 250 newtons per meter. All right, we'll try that. Okay, so what we're going to do is we're going to try and find out how fast is the car going at the very top of its path after it goes over the ramp. Now, this is just a conservation of energy question. We've got different types of energies going on. Over here, we have elastic potential energy. And that's all we have up here. It shoots. Here it's all kinetic energy. And then it goes over the ramp. And up here it's still moving. So there's kinetic energy here. But since it's off the ground, it also has gravitational potential energy. And all of these energies, whether it's here or here or here, all those energies would be equal. Total energy here has to be equal to the total energy here. It's all kinetic, equal to the total energy here. So once again, if I've got the total energy at one place, I have it everywhere. Now the only place I can find the total energy is in the elastic. So I'm just going to start with that. So if I find my elastic potential energy at the very beginning, so that's my 1/2 kx squared expression. I've got my 1/2, I've got my K value of 250, and then I've got my 5 centimeters. Don't forget to change that to meters, and don't forget to square it. We've got 0.3125 joules of elastic energy inside the little launcher. Now, if I wanted to, I could actually take this and put it here to find out the initial speed. I could find out how fast it was actually launched out of the Hot Wheels launcher. But I'm more concerned right now about trying to find the speed at the very top. So at the very top, we've got combinations of energies. We've got kinetic and potential. So I can't find the kinetic energy at the top, but I can find the potential because I've got the height and I've got its mass. So if I find the potential energy, the gravitational potential energy at the top, to see what I've got the mass of the car. That's my 0.035 kilograms. Don't forget to change that to kilograms. I know gravity, of course. And I've got my height of 20 centimeters. We've got potential energy of 0.069 joules. All right. So I know my car came in with this much energy. That's my total energy it started with. At the top of the pathway, it's got this much potential energy, which means the remaining energy has to be my kinetic energy. So to find my kinetic energy at the top, all I have to do is do the 0.3125. We'll take away how much was potential energy, and that is going to then leave me with how much kinetic energy I have. So we'll just take the difference between the two, and we'll do a little rounding off here already. We've got about 0.244 joules of kinetic energy. So these two put together will still add up to how much I started with. Well, now that I have the kinetic energy at the top, I can find out how fast it's going at the top. I just take that kinetic energy, I'm going to times that by the 1/2, and then divide that by the mass of the car, which of course was 0.035 kilograms, Now, once again, don't forget to square root, and we've got a speed of approximately 1.9 meters per second, which is how fast it would be going at that location. So once again, conservation of energy, find energies, total energy never changes. Sometimes you have a combination of energies, but they'll still add up to the total. Just find energies wherever you can, find what you're missing, and then sort of just piece things together.